Good morning, students. Welcome to the next topic, second class on the topic capacitors. In the last class, we discussed some introductory ideas regarding the capacitors. What are they? How can we construct a capacitor? So before proceeding further, let me summarize what we had discussed in the last class. So capacitor we had discussed, it is nothing but a pair of metal plates, conducting plates, which are connected to a battery. If you connect it to a battery, charges will redistribute, charges will flow. One of the plates will acquire positive charge, say plus Q, other acquires negative charge minus Q, and then after charging, this process is called as charging of capacitor. After charging, we can remove the battery. We can disconnect the capacitor from the battery, and we say that the capacitor is charged. And we say that Q is the charge on the capacitor, its capacitance is C, and the potential difference between the plates of the capacitor, we say it is how much? V. And we had discussed that this Q is proportional to V, and then we write Q is equal to some constant times V. That constant we had written as C, which we call as capacitance. And if you remember, students, its SI unit I had discussed as farad, but it is large unit, so we talk about microfarad and so on. Next, we had discussed how to calculate the capacitance of a parallel plate capacitor. If we have a parallel plate capacitor and each plate has surface charge density plus sigma and minus sigma, A is the area of the plate of the capacitor, and in between the plates of the capacitor there is vacuum. We can approximate it to air also. Then the electric field between the plates of the capacitor is found to be in this direction, from the positive plate to the negative plate. Outside this, in the region outside the plates of the capacitor, that is in this region and in this region, the electric field is 0. And in between the plates, the electric field is given by the formula sigma upon epsilon naught. I had discussed this in detail in the last class. Potential difference between the plates of the capacitor will be electric field times this distance, that is d, E naught times d. Now E naught is our sigma by epsilon naught, and sigma can be written as charge per unit area, Q by A. So how much this becomes? V will become E naught d, that is Q upon A epsilon naught times d. So V is this much. Capacitance by definition is Q upon V. So C, which is Q upon V, we have derived this relation and we had got this much. This d is in numerator, E naught times d. So C is Q by V, that is A epsilon naught upon d. This was the capacitance of a parallel plate capacitor. Now after that we had discussed effect of dielectric. In between the plates of the capacitor, if there is some dielectric inserted whose dielectric constant is given to be K, then what changes do we find in these parameters? First, the electric field between the plates of the capacitor gets reduced. The new electric field will be E naught upon K, and this was discussed in detail in the last class. So E naught by K means it becomes Q upon K times A times epsilon naught. Remember, K is greater than 1. That's why I am saying electric field is reduced by a factor of K. Then the potential difference between the plates of the capacitor will become the new electric field E times D. And that becomes how much? QD upon KA epsilon naught. And therefore the new capacitance, if the original capacitance I write as C, the new capacitance I write as, original one I write as C naught, the new capacitance C will be Q upon V, and that will become how much? You can see Q upon V will become A epsilon naught upon D multiplied by K. And this we can write as, you can see A epsilon naught by D is nothing but C naught, so I can write K times C naught. So what do we find? We find this you should write in the statements also on comparing. The electric field is reduced by a factor of K. the potential difference between the plates that is reduced by a factor of K, and capacitance of the parallel plate capacitor is increased by a factor of K. Having summarized this much, we will proceed to some more details regarding this capacitor. Let's see one by one. Okay, let's see. This is a capacitor. The separation between the plates is D. In this capacitor, there are two dielectrics of thickness T1 and T2 and dielectric constants K1 and K2. And this is vacuum. The area of the plate is equal to area of the first dielectric, and that is also equal to area of the second dielectric. The dielectrics have different thickness T1 and T2. They have different dielectric constants also K1 and K2. We have to find the net capacitance. Let's see how to do this question. First step, you remember, you should find potential difference between the plates of the capacitor. And for that, you should use the formula V is equal to E times D, where E is the electric field and D is the separation between the D is that region over which that electric field is operating. Second step, C is equal to Q upon V. Actually, this would be second step. This is third step, and the first step is to find E in different regions. These three steps, if you keep in your mind, you can solve for such questions. Let's see one by one. First step, you have to see for electric field value in different regions. In absence of dielectrics, if there were no dielectric, there was only vacuum, the electric field will be denoted by E naught, and that you know, students, that is given by sigma upon epsilon naught, where sigma can be written as Q upon A epsilon naught. Sigma is surface charge density, you know these things. This is in absence of dielectric. So here in this region where there is vacuum, the electric field will be E naught. So I will write here E naught. Now in these two regions, the electric field will not be E naught. We have already discussed, due to presence of dielectric, the electric field gets reduced by a factor of dielectric constant. So in this region, the electric field will be how much? It will be E naught divided by this dielectric constant, that is K1. Is it clear, students? And in this second medium, the electric field will be E naught divided by this dielectric constant, that is K2. So let me repeat, what are the electric field in different regions? For this first dielectric, within this, the electric field will be E naught by K1. Then in the next region, for thickness T2, the electric field will be E naught by K2. And in the third region, there is no dielectric, so electric field will be E naught, where E naught is how much? Q upon A epsilon naught. So this is our step 1. Next we have to think about the step 2. Step 2 is calculation for potential difference. So potential difference is the potential difference between the positive and negative plates. So I can write it as V plus minus V minus. If I name these points as 1 and 2, this point I call as 1, this point I call as 2, suppose. Then V plus minus V minus, I can write it like this: V plus minus potential of point 1 plus potential of point 1 minus potential of point 2 plus V2 minus V minus. You can see these two terms can cancel, these two terms will cancel, we will be left with V plus minus V minus, that is what we wish. Now I will segregate these three terms. What is our V plus minus V1? This is the potential difference between these 2 points. Between these 2 points, what is the electric field? It is this much. So we will write E naught by K1. Remember, how do we find potential difference? electric field multiplied by the distance. If it is uniform, then here the fields are uniform. So E naught by K1 into that thickness. What is this thickness? T1 plus. Likewise, you can guess, students, what should we write here? This will be E naught upon K2 times T2, and third one will be E naught. So can we take E naught common? Yes, we can do. So E naught, and E naught we can take common. We will be left with this much. And how much is E naught? Our E naught is Q upon A epsilon naught. So this is our V. And therefore capacitance, what formula we have to use? Q upon V. You can see this is Q, this is V. So A epsilon naught will come this side and divided by this entire thing, that is T1 upon K1 plus T2 upon K2 plus, here I have missed one term. There is a mistake over there. This V, here I have to multiply electric field with distance. The distance was T1 here. The distance was T2 for second case. For third case, what is this distance? It is this total distance minus this plus this. So that will be, so Q upon A epsilon naught, I will write at far. So V2 minus V minus will be E naught which I have taken common into this thickness. This thickness is how much, students? That is D minus T1 plus T2. So now we get T1 upon K1, T2 upon K2 plus this last one, that is D minus T1 plus T2 upon nothing, that means 1. This is the answer to the question. How do we remember this? Let me make it very easy for you to remember. Whatever capacitor is given, this part has dielectric constant K1, this part has dielectric constant K2, and this was having vacuum. Suppose it is not vacuum, it is K3 also. Let me make it more general. And let the thickness be T1, T2 and T3. Without any dielectric, the formula would have been how much? A epsilon naught upon total thickness. But here dielectrics are present, so the thickness you will divide into three parts here: T1, T2 and T3. And all the thickness you will divide by the corresponding dielectric constants. So T1 by K1, T2 by K2 and T3 by K3. Is it clear, students? T2 upon K2, T3 upon K3, and we have to add them. This will be the total value of capacitance, A epsilon naught upon T1 by K1 plus T2 by K2 plus T3 upon K3. This is as indicated over here. Here we have the capacitor, same K1, K2, K3, T1, T2, T3. The total capacitance is given by this particular formula. Now if one of them is vacuum, suppose this region is vacuum, then also the same formula you have to use. Remember, students, K is equal to 1 for vacuum. For vacuum, the value of K is 1. If it is vacuum, instead of K3, you should put 1. So it will become T3 by 1. That is the answer to our question. Is it clear, students? Okay. Based on this particular discussion which we had, you can try to solve example 2.8 of your NCERT textbook. Please don't see the solution given in the textbook. You try to do it yourself. You will be able to do it. Let us proceed to discuss some more things. We will discuss series combination of capacitors first. Suppose we will take help of two capacitors. Suppose this is capacitor which has capacitance C1, and this is second capacitor which has capacitance C2. One of the plates of capacitor C1 will connect to that of C2 like so. Now the unconnected part plates of capacitors C1 and C2, we will connect them to a battery. Like so. So this is series combination of two capacitors C1 and C2. The instant we connect a battery, now this battery has this positive and this negative terminals. It will send minus some negative charge and it will send some positive charge. So this plate, right plate of capacitor C2 will develop some negative charge, say minus Q, and likewise this will attain some charge, say plus Q. The magnitudes will be same because they are connected by the same battery. Actually, it is the flow of electrons that take place. The positive plate of this battery, it attracts the electrons. Now from where do the electrons come? Remember, these plates of capacitors are metals. Metals have large number of free electrons. So those free electrons from the metals, they move through this wire to this positive terminal of the battery. So electrons will move like this. Likewise, from negative charge of this negative plate of the battery, electrons move to this particular plate, but they don't have any path further. So these electrons come and they accumulate on this plate. So the effective result is that the left plate of capacitor C1, it loses electrons, and the right plate of capacitor C2, it gains electrons. So it acquires plus Q charge, it acquires minus Q charge. And this takes place very quickly, within fraction of seconds. Once they get charged, you can disconnect the battery. Then flow of electrons, when the flow of electrons is stopped, you can disconnect the battery. In this combination, these two plates, do you think they will remain uncharged? No. You see these negatively charged electrons which accumulate here. Here they have negative charges. They will repel these electrons, free electrons on this plate. So the free electrons on this plate will move and they will accumulate on this particular plate. These free electrons on this plate are repelled by the negatively charged plate. Also, they are attracted by the positively charged plate. These are having positive charges. Is it clear, students? So these electrons will be moving from this plate to this plate. So this plate will lose electron. Hence, it acquires what kind of charge? Positive. And this will acquire negative charge. Since the electrons are moving from this part to this part, it is clear that if it is plus Q dash, this also must be minus Q dash. They must have same magnitude. This Q dash is found to be equal to Q. So I'll write it as plus Q and I'll write it as minus Q. This is very important. Now why is it so? In equilibrium situation, this charge on these plates will be identical. It is so because if you remember, students, while discussing the capacitor, one of them has charge plus Q, other one has charge minus Q. So the surface charge densities are plus sigma and minus sigma. We have discussed in these regions outside the plate, the electric field was how much? 0. And here the electric field was sigma upon epsilon naught. Why was this electric field 0? Because these two plates were having identical surface charge densities. Sigma by 2 epsilon naught towards left and sigma by 2 epsilon naught towards right were the values of electric field. So the net electric field was 0. Similar is the situation here. If these charges are not plus Q and minus Q and are a bit less, then these two charges will not be equal and opposite. So net charge on this capacitor will not be 0. If net charge on this capacitor is not 0, net charge on this capacitor is not 0, then means these two charges are not equal and opposite. If they are not equal and opposite, these two factors, sigma by 2 epsilon naught and sigma by 2 epsilon naught, they will not cancel completely. One of them will be more, one of them will be less. That means the net electric field outside the plates of this capacitor, that means in this region, the net electric field will not be 0. And if electric field is not zero, then see this blue one. What is this? This is a metallic wire. It is used for connection. Since this is a metal, it has free electrons. Under the influence of non-zero electric field, electrons will flow. But we are discussing static situation when there is no current. So since there is no current, charges cannot move. Charges cannot move means there must not be any electric field. If there is supposed to be no electric field in this region, there is only one possibility: both these plates must have equal and opposite charge. Both these plates must have equal and opposite charge. On account of this particular reasoning, we say the net electric field here in this particular region must be how much, students? 0. And for this electric field to be 0, the charges must be plus q minus q, again plus q and minus q. Remember, the total charge on a capacitor must be 0. This is plus q, this is minus q, it has to be 0. If it is not 0, charge will flow. Why charge will flow? Because if it is not 0, electric field will not be 0. If E is not 0, the free electrons in the connecting wires would flow. I would suggest you to listen to this particular explanation again, and if possible again, and write this explanation in your note. You can find this explanation in your NCERT text also. Let's proceed further regarding this. So what do we find? That in series combination, charge on each of the capacitor is same, Q, Q. Remember, net charge is 0, but we say this capacitor has charge how much? Q. It is just a matter of terminology. Let V be the potential difference of the battery which we have used to charge these capacitors. Let the potential difference across the first capacitor be V1 and across second capacitor it be V2. Potential difference means this potential minus this potential. Let me call these points as 1, then 2 and then 3. You see, this point 1 is connected to this positive terminal, 3 is connected to this negative terminal. So I can write this V. What is V? V is V plus minus V minus, difference of these two potentials. But since this point is connected to point 1, I can write V plus as same as V1. Likewise, V minus, potential of this point must be same as potential of this point. Now this I'll modify a bit. This can be written as V1 minus V2 plus V2 minus V3. You can see minus V2 plus V2 will cancel, and we will be left with V1 minus V3. Now we will separate these two. Now what is V1 minus V2? Now for each capacitor, for capacitor C1 and for capacitor C2, we can write some basic equations. What are those equations? Charge on this capacitor, that is Q, is equal to its capacitance, that is C1, times its potential difference, that is V1. Q is equal to C1 V1. Likewise, here we will have Q is equal to C2 times V2. So V1 minus V2 is nothing but V1. Oh, sorry. I should change the terminologies a bit. I should not have used points 1, 2, 3. Let me call them as points A, B and C. I already have used V1 as separate symbol. So instead of 1, I will write it as A. Instead of 3, I will write it as C. Just a matter of choice of symbols. So VA minus VB and VB minus VC. Now you see, VA minus VB is nothing but this potential difference, which we will write as V1. And VB minus VC is this potential difference, which we write as V2. Now V1, you can see, students, V1 will be how much? Q upon C1. And V2 will be how much? Q upon C2. So this is our V. So V is equal to Q upon C1 plus Q upon C2. So this implies I can write V, you can take Q as common, 1 by C1 plus 1 by C2. If we wish to find the net capacitance of this combination, so we use some symbol, say C. Let C, and for series combination let me put a subscript S. Let CS be the net capacitance of this combination. That net capacitance means you remove these two capacitors and put a single capacitor whose capacitance is how much? Cs. Then on it the charges will be plus Q and minus Q, and the potential difference remains same. If Cs is the net capacitance of these two capacitors, then I can write the charge on this capacitor Q is equal to Cs times V, and this implies V will become how much? Q upon Cs. Now these two equations we can extract some information out of them. So from 1 and 2, you see their LHS are same, V and V, so their RHS must be same. So we'll have Q by Cs is equal to Q into 1 upon C1 plus 1 upon C2. So Q will cancel and we will be left with this particular formula, which you should remember, you should commit to memory, that if we have series combination of two capacitors, the net capacitance Cs is given by this formula. 1 by Cs is equal to 1 by C1 plus 1 by C2. Instead of 2, if we have 3 or more capacitors, just we'll have more terms. 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Next we discuss parallel combination of capacitors quickly. Here we have two capacitors connected in parallel and they are charged first using some battery. This battery will send some charge. You can see clearly that charge will distribute itself between these two capacitors. In series, all the capacitors had same charges. That will not be so in case of parallel combinations. If this battery sends charge Q, out of charge Q, something will flow through this capacitor, something will flow to this capacitor. Let here the charge be plus Q1 and here the charge be plus Q2. Same thing we can expect from the negative terminal of the battery. So here the charges will be minus Q1 and here the charges will be minus Q2. Remember, the net charge on the capacitor must be 0 and the total charge will be Q1 plus Q2. So total charge or net charge, you can write it as Q1 plus Q2. Second important thing that you should note in parallel combination, you see this plate and this plate. The left plates of both the capacitor are connected together. That means they will be at same potential and that will be equal to the potential of this positive terminal of the battery. Likewise, the right plates of both the capacitors are connected together and they are connected to the negative terminal of the battery. So all these three, the right plates and the negative terminal, will have same potential. Therefore, this potential difference is same as potential difference between these 2 points, which in turn is same as the potential difference between these 2 points or these 2 points. So the potential difference between the plates of the capacitor will be same in case of parallel combination. So we'll have V and V. Thus, for capacitor C1 and C2, we will write the equations like this. Charge Q1 is equal to C1 times V, and for C2 we will write charge Q2 is equal to C2 times V. Is it clear, students? The equivalent capacitor has charge how much? Q is equal to Q1 plus Q2. The equivalent capacitor means I can draw it like this. It has capacitance C, which we have to find, and it will have charge how much? Plus Q and minus Q, where Q is equal to how much? Q1 plus Q2, and the potential difference remains same. So this implies Q is equal to Q1 will write as C1V, Q2 will write as C2V. So V you can take common, that is C1 plus C2 into V. But as you can see, for the equivalent capacitor, the equation will be total charge Q is equal to net capacitance C. Now because they are in parallel, I can write Cp. So I write Cp times potential difference, that is V. Now these are equations 1 and 2. We can compare these equations to get the result. You see their LHS are same. So we'll write Cpv is equal to C1 plus C2 into V. So V cancels and this gives our result Cp is equal to C1 plus C2. So let me summarize what we have discussed so far. We discussed today the series and parallel combination of capacitors. So if we have series combination, then the net capacitance, its reciprocal 1 by Cs, S for series, is given as 1 by C1, 1 by C2, 1 by C3, depending upon how many capacitors you have used. Number 1. Second, in parallel combination, the net capacitance Cp is just given by the sum of the individual capacitances. C1 plus, C2 plus, C3 plus, so on. Okay students, I'll stop here. Read well. Thank you.